Structural Modeling 2.0, an application of basic structural modeling and interpretive structural modeling. This is our next cut at structural modeling videos. We have improved technologies and a whole new video development suite. The information is located on my website. It has a lot of background information on the structural modeling project. This is where there's documents, there's other videos from the first video series, and there's a complete archive. When you go to the front, this archive right here will take you back into all the historical data. There's a pointer to the SAGE tool that was used in the first videos. This video uses a JavaScript tool. And then this is pointer to my Twitter account where I make announcements of new videos and other types of information as it becomes available associated with a project. So let's move right on with this. So the basic structural modeling project, we're starting into the phase 2 video series. The phase 1 video series is complete. We're going to go over and develop some fundamental concepts and ideas, which we'll go over again in this video, introductory video. And I've developed a JavaScript web application that I will introduce in this introductory video here for the second series. And we'll talk a little bit about the inference operation and application, and also structural integration modeling, which is a component of structural modeling which fits between basic structural modeling and interpretive structural modeling. So the phase 1 video series had graphic grids that were created using a spreadsheet. The graphic analysis was performed manually. Matrix calculations were performed in a SAGE program, and then the manual transfer of data between the SAGE and the spreadsheet. So there was limited inference integration points because it was done manually, and it was used to test the video production capability. I used a Linux-based system the last time. This time we're using an Apple-based system. We'll see how it goes. It was a good start, but it really needs some improvement. So we'll see if we can do that here. The phase 2 video series, we had created a JavaScript program for automation of an integration of the activities. The graphic grid is drawn on HTML5 canvas. The matrix calculations are performed by JavaScript, and all the information is in one program, so there's no need to transfer data between one system and another. And the integration analysis is available at every step. You can just click the infer information and see if there's any new information available. And of course it's used to demonstrate the JavaScript program that is just kind of a proof of concept here, and it shows the types of systems that can be developed. So the fundamental concepts and ideas, basically what we're focusing on here is the 3 types of truth: the formal truth, the factual truth, and the value truth. And in the grid that we're using here, we're using the grid as a component of the marking space in the art form, and we are encoding formal information and factual information both in that grid. And so this approach uses the same computational system and demonstrating a computational approach with an open source tool. So we're using, of course, JavaScript, HTML5, other types of open source tools are available. The application relation type integrates with the truth operations. We're integrating the formal and factual truth into the marking space. The value truth will be used in the value space. We won't be using that much in this particular series, but that may become important later on. And of course the value space supports the value truth. And system structure, of course we need to think about what a system is and how it relates back to these components. So the types of truth, there's a formal truth, which just depends only on the logical connectivities in the sentence. You can do computation, they're certain, they have some nice qualities to them. There's factual truth, which depends on the state of the real world. Of course, then there's value truth, which can be determined in a number of different ways, but is really dependent upon the value system associated with an individual or an organization, and it really expands into ethics, culture, and prediction type of issues. So here's a chart that kind of gives an overview of these three types of truth. And what we're going to be doing is we're going to be combining the formal and factual truth into the marking space using this grid. And we'll see that the formal truth is really not known by experience, but it's certain. Factual truth is known by experience, but it's not certain. And the required data to validate inference, of course, is a proof, so you can calculate it. And observational data and predictive success are what's important in the factual area, with empirical data that's integrated and entered into the program. So we'll see this as you go forward, how these components all work. Abstract relation type, which was developed by the authors, essentially has three primary areas. It has a marking space, an outcome space, and a value space. Each of these spaces can have one or more matrices associated with them or other subspaces associated with them, and they're used to encode specific types of information. In this case, we're going to be encoding the factual and formal truth in the marking space matrix. We'll have one matrix, and it will be in the marking space, and that's what we'll be focusing on at this time. Then the abstract relation type, which has three types of information associated with it: the prose information, graphics information, and mathematics and computer representation. The documents on the website associated with this video series details this in particular, but we're going to be working on the math area here, of course, in this computer code. And we're working with systems and system concepts. We normally work with them in two modes, either the design mode or the discovery mode. And in this specific case, we're working in the discovery mode. We know they're objects. We know we have these 19 cities, and we need to discover the relationships between and among these objects. This is a graphical type of approach. Now, most systems, a graphical type of approaches work in the design mode, where they use the graphics to document and communicate the aspects of the system design. So this type of graphical approach is a little bit different. So a system is a relationship mapped over a set of objects. We know the cities, those are the objects. We know the general relationship is north of, but we must discover the specific relationship between each city pair. And that way we'll have empirical data, and once we get empirical data, we'll also infer relationships from the already collected empirical data, which will help us complete the task more efficiently. And to create a Java, so the conceptual design objectives basically create a JavaScript-based ordering process, which we've done, we'll demonstrate here. We'll integrate graphic, inference, and analysis into the same program, create an integrated tool base, and of course key design considerations are maximize use of inference, minimize the use of empirical data, and minimize costs, because gathering empirical data, of course, costs money, and demonstrate the JavaScript application. So the general steps in this process, basically step one, you initialize the process, which is identify the cities, create the matrix. And then general step two, which you just loop through until you're done, is to obtain empirical data, order the structural information, infer additional information, and then goes back up to step one, which is obtain more information. You cycle through this until you have a completely ordered system. And on the matrix, when we're integrating and using two types of truth, we have specific marking process. So this is the specific process marking types. So we're using, for formal truth, we use true and false. For empirical truth, it's either known or unknown. And we can combine these and use them on the same matrix, we're using true, false, and unknown, because true and false are known. And for our green backgrounds in cells is true, red backgrounds is false, and yellow backgrounds in our cells means unknown. This is our structural modeling grid. This is the main canvas. It has a city name tag canvas and a city name tag canvas here. And you start by pressing the initial city grid button, and you then get an initialized grid which has all yellows with unknown information. Of course, we don't have any information yet, but we see we have red here, so we know something for certain. And what this says is city 2 north of city 2, and that's 0 that has a red background, which means false. And we know that logically because we're not going to allow a city to be north of itself. So we've done this quite a bit here, and everybody on the diagonal then is not allowed to be north of itself. Is city 18 north of city 18? No, we don't allow that. So those are all false, and everything else is unknown. We really don't know the relationship for any of the other cities. So we start by entering data on city 4 and 16. We go gather some information. We know that city 4 is north of city 16. We enter them into the grid, and then these buttons appear, and we observe the grid, and we say green is in the lower section down here. So we press the green in the lower section button, and then these buttons go away. We go and select the lower section button and press it, and that goes away. And then we start working on city 3 and 5. So we enter city 3 and 5. So here's city 3, city 5. Again, green is in the lower section, so we press that button. Then we enter city 4 and 2, city 4 and city 2, and now green is in the upper section. So we need to select green in the upper section. Once we do that, we see that city 4 and city 2 have been swapped, and now the green is in the lower section of the matrix. Then we'll enter city 2 and 1, and now you see the green is again in the upper section. So you select green in the upper section, and that moves the 2 and 1. But now we have 4 green is in the upper section, and we didn't enter that. That came out of the process. So we need to select the process data button right here, and then pops up another entry screen, which is move city data. We enter the city 4 and 2, like here, like we need to do. Enter city 4 and 2, press the move city button, and the cities are then swapped, and the green is in the lower section. So now we'll press the infer information button and see if there is some inferred data that we can get from that. So we go ahead and do that, and yes, there is inferred data. We can see here that there's a blue background in this particular case. So we have enough empirical data now to allow us to start inferring types of data points in the matrix. So the JavaScript inference operation basically uses unique JavaScript matrix functions, and the inference function is readily available. It's just a button that you press on the web app, and marks inferred information with a blue background, and it's integrated completely into the program. There's no transferring between two different programs. So structural integration modeling is a component of structural modeling, and there's basic structural modeling and interpretive structural modeling, and the structural integration modeling fits in between these two and creates a framework that enables the communication and documentation of structural integration modeling methods and techniques, or what you do with the basic structural modeling components to create interpretive structural models. So this is an area where we're developing that more. So that's the beginning of the end of the beginning of the new series, and we'll have more data and more videos in the coming weeks.